Hey, so you had homework. Your homework was the day 8 and 9 homework on inverse functions, and you were to do all of them. So let's start here with number 3. Um, your instructions are bad. Your instructions are telling you show that the given function is 1 to 1 and find its inverse. So show that it's 1 to 1. That's not super obvious. How do you do that? So how do you show? Well, like everything else we do, I would ideally like to hit those 3 prongs: numerical, algebraical, not algebraical, numerical, algebraic, and graphical. Maybe algebraical is a word. Algebraically is certainly an adverb. Anyway, I don't care. Um, I don't really care. To show that this function is 1 to 1 algebraically is weird. I don't care. To show that it's 1 to 1 numerically is weird. I don't care. I don't want to do it. I think falling back on our understanding of the graph is fine. So what does that mean? It means we could go to Desmos or whatever other grapher you got. Ignore the blue. The blue is our inverse function, but there's our function in red. You guys know that it's just a line, right? It's a linear function. And so clearly it's going to pass that horizontal line test. That makes it 1 to 1. If you can construct that argument, I'm fine. I'm happy. Any linear function is always going to be 1 to 1 because it passes that horizontal line test. That's it. I'm convinced. Let's move on. So now that we've shown that it's 1 to 1, we'll find its inverse. Then we'll check our answers algebraically and graphically. Okay, let's verify that the range, sure. So to find the inverse, we're just gonna switch our variables like we always do. So f of x being our y variable, it becomes x. And x minus 2 over 3 is going to become y minus 2 over 3 plus 4. And this thing being linear, the math here should be simple. We're going to subtract 4 from both sides. We get x minus 4. We're going to multiply through by 3. So we get 3 times x minus 4. Then we would have to add 2. And that's y. Should you be able to do all those steps in one fell swoop? Yeah, I think so. So y is going to be the inverse of f. And yeah, I'd clean this up. You can distribute the 3 to get 3x minus 12 plus 2 equals y. So that means 3x minus 10 is equal to our inverse function. Now there's a handful of tests we're supposed to do. The first test would be just to verify that the domain of the original function, which is all reals, that should be the range of our new function. And of course it is, because this function again is just a line. So you know that the range of the inverse function will be all reals, which is good because we needed the domain of the original to become the range of the inverse, and it did. And this is a very boring example in terms of domain and range because this linear function's range was all reals, which is very convenient because now our inverse function has a domain of all reals. So it did say to do that somewhere. Verify that the range of function f is the domain of f inverse. So we verified that. Now it also says we're supposed to check our answers algebraically and graphically. So checking that these things are inverses graphically, we would go to Desmos. And I would just graph them together. And I might want to graph the line y equals x. And when you graph them together, you can see that yes, they are reflected images of one another. You could maybe look at your intercepts here. And that helps to kind of verify that yes, these functions are inverses of one another because we see that input-output switching, right? We can see that. What else could we do? If you're fancy, if you understand Desmos pretty well, then you can click on the little cog and then you can copy this function and turn it into a table of values. Then you can do that again. Let's take the blue function, copy it, turn it into a table of values. And then I guess the way we would do this is if these things are supposed to be all flipped, then we could check, hey, 2.666666666 is mapping onto -2 like it's supposed to, so those are flipped. 3 is mapping onto -1 like it's supposed to. 3.333, let's just be normal here. That's what, 3 1/3, so 10/3 is mapping onto 0 like it should. 3 2/3 is 11/3, right? Which is mapping onto 1 like it ought to. And 4 is mapping onto 2. So this is sort of a numerical approach to verifying that our two functions are actually inverses. You're just showing that, these 5 ordered, and again, I'm just taking these 5 ordered pairs because it's what Desmos gave me. There's nothing sacred about it. But those 5 ordered pairs, when reversed, do become 5 ordered pairs of the other one. And the 2.666 is bothering me now. What is that? 2 2/3, so 8/3. I'm going to enter that as 8/3. But we still see it because -2. The nice thing about that is Desmos will actually plot those points too. So you can actually see that 0.24 becoming the 0.42. We can see that reflection across this line. Yeah. And, you can see that in all these other points too. 1, 3 becoming 3, -1. So that's nice. So you've got your graphical approach. You've got the numeric approach too. You can kind of embed that right into the Desmos and see it. The algebraic approach, of course, is everybody's least favorite part. But the algebraic approach is when we're supposed to actually test the converse. Sorry, the composition. I don't know, I said converse. So we're supposed to now test that f composed with f inverse. That had better give us plain old x. But that's not good enough. We also need f inverse composed with f to give us x. So without further ado, let's do it. We're going to take the inverse function and plug it into the original. So we get 3x minus 10 gets substituted in for x. So we'd end up with 3x minus 10, some parentheses just as a placeholder. And then there's the -2 all over 3 plus 4. So there's our composition. We can clean this up. The -2 can just combine with the -10 because again these parentheses are really just placeholders that aren't really separating anything. So now we're looking at a 3x minus 12 over 3 plus 4. And I'm sure we all remember that when we divide this binomial by 3, it's both terms of the binomial getting divided by that 3. So that's going to reduce down to an x minus a 4. And then, of course, there's a plus 4 on the end, which conveniently cancels. And the whole thing boils down to x, like it should. Then we do the same thing, but in the other order. So this time we're going to take all of f of x and plug it into the inverse function. So we'll have 3 times the original function f minus 10. And that whole thing should boil down to x. So the original function is x minus 2 all over 3 plus 4. So to clean this up, I suppose you would start by distributing in the 3. So when the 3 hits the first term, the 3's just cancel and you get x minus 2. And then the 3 distributes onto the 4 and gives you a plus 12. And then you've also got a minus 10 on the end. So minus 2 plus 12 is, of course, 10. And then the minus 10 will cancel. So all of those constants cancel, and we do boil down to plain old x. So there's your algebraic proof that f and f inverse are truly the inverse of one another. I showed you on Desmos the graphical proof because they were reflected images over the line y equals x. And again in Desmos also, we kind of embedded a numerical justification for the functions being inverses. And again, this was not a numerical proof, but it was some evidence, and I didn't realize my stupid face was in the way, so you can just move that. There you go. Now you can see those tables of values. But you can see that these ordered pairs are just flip-flopped. We've got the -2 and the 8/3 becoming 8/3 -2. We've got, I can't really read this. -1, 3 becoming 3, -1, etc., etc. Okay? Anyway, let me put my big dumb face back. All right. Is there any value to having my big dumb face, by the way? Or would you rather just have me talking as a voiceover? I don't know. I feel like my big dumb face gives the video a little more visual interest. I could be wrong as I scratch my cheek. All right, let's go back. I think I'm done with number 3 and I'm happy with it. That was a very thorough treatment of this problem, and hopefully talking very in depth about an easy function means that when we get to the harder one, you'll understand it better. So let's do number 6 now. This is a radical function. Let's see how this goes. Again, the first thing we're supposed to do is just verify that we're one-to-one. And ideally, the best way to do that would be just to picture the graph. And again, ideally, you can sketch this graph yourself without having to go to Desmos. It's not necessary, but maybe you would rather see this 2 on the end. So maybe this would be better thought of as a root x minus 5 that just has a negative coefficient, causing it to reflect over the x-axis. And then this 2 that's in the front could just as well be thought of as a 2 that's at the back. And then maybe this jogs your memory better, that plus 2 is a vertical translation 2 units up. And of course the minus 5 inside of the radical is a translation 5 units to the right. Okay, so once we get all that, we can see that our parent function would have been a sort of half parabola emanating from the origin and opening to the right. So just apply these transformations. We're going to get translated 5 to the right and up 2. So this now would be sort of our vertex, so to speak. And normally we would open to the right, and we still open to the right, but we got reflected over the x-axis. So this thing is going to actually be sort of the bottom half of the parabola instead of the top half. But there's your sketch. Hopefully you guys can puzzle through that just as well as I can. You're supposed to know that. We could, of course, go to Desmos and just verify. And oh, look, there it is. We are, in fact, chilling. I can't make that point stay forever. I mean, you can always cheat. We can just say, hey, put a point at 5, 2. And I want that point to be red. But there you go. We can see that that point wants to be at 5, 2. And we can see that the graph wants to be reflected down. And so, yeah, that's our graph. And it surely passes the horizontal line test. So we are definitely one-to-one. So I'm happy going back now. And from this graph, we can very easily tease out our domain and range. The domain is just from the vertex to infinity. So 5 gives 0 under the radical. And then if we want that radicand to be greater than 0, then we know we need x to be greater than 5. So it should be obvious to everyone that 5 is sort of the cutoff. And it should also be obvious that we only want values greater than 5. 5 itself is acceptable, so we go hard bracket 5 to infinity. Now the range is going to be born of the 2 here, and also the fact that we got reflected. So we can see that 2 this time is not our minimum value, but our maximum value. So our range is going to want to be coming up from negative infinity with 2 as a max that is included. So there's our range. Again, from the graph, it's quite easy to see that range. Ideally, from the function, it would be easy to see that too, because you would think about how well the graph is reflected, so it'll be negative infinity up to some maximum value, and then that maximum value is 2 because the whole graph got shifted up by 2. All right, so there, we did it. What are we trying to do? We sort of showed that we're one-to-one just by appealing to our knowledge of the graph. We're one-to-one because the graph passes the horizontal line test. We want to now find our inverse algebraically. That means just swapping the variables. So f of x becomes x, and the function becomes 2 minus the square root of y minus 5. And now you're just doing algebra, so you're going to subtract the 2 you get x minus 2 equals negative root y minus 5. I would multiply through by negative 1 or divide through by negative 1, whatever feels more natural to you to get rid of a negative. But this guy will become negative x plus 2, and that'll equal the square root of y minus 5. We are now squaring on both sides. And another trick we might do here is, I don't like these leading negatives. You guys have heard me say that a bunch. So just flip the order. This could become 2 plus negative x, aka 2 minus x. And that's cleaner. And we're squaring that. And that now cancels this. We get y minus 5. Then we're going to add 5. So that's y, which means that's our inverse function. But before I throw a box around this, we should probably stop and think for a second. This quadratic function, right, we're supposed to verify that our range is equal to the domain of the other function. Well, this guy's domain is only 5 to infinity, but this function's domain, as written, would be all real numbers. We don't want that, right? We don't want the inverse of our half parabola to be a full parabola. So we know that we actually have to restrict the domain on this function. So really, when we state our inverse, we kind of need to build that restricted domain right into our statement. So the 2 minus x squared I'm happy with, plus 5 I'm happy with, but then really we should be saying comma, and we should be restricting our domain to only the stuff that we actually want. And I guess what? Let's go to Desmos to look at that, I guess. But we just said we wanted the function 2 minus x all squared plus 5. Okay. Again, when we're talking about inverse functions, you want to always have the line y equals x in mind as well. So let me turn that. I think black is good. This I want blue. Yeah, and that's fine. So maybe you can tell that this bottom half of a parabola, when reflected, it actually corresponds to the left side of our parabola. So when I restrict this parabola's domain, I don't want the stuff that goes from 2 to infinity. I want the stuff that goes from negative infinity to 2. I want that left-hand side, right? We can see that. Because we have the bottom half of a parabola in our radical, we want the left-hand side of this parabola from our quadratic. And guess what? That should have made perfect sense to you anyway, because guess what? We already knew that we needed the domain of our inverse function to be the range of our original. So we knew that what we wanted was negative infinity up to 2 rather than 2 out to infinity. So I think when I write my restriction, I tend to write it as an inequality. So instead of giving it an interval notation, I would just say here, we only want the x's that are less than or equal to 2. But it is important that you build that restriction right into the statement of the function. Otherwise, people are going to look at this function and think that the domain is all reals. If you want that restriction to be something that people know you're considering, you have to write it right in there. Now, on the other hand, we are still going to give the domain too. So f inverse and the range of f inverse. And the domain is just going to be the range from before, so negative infinity up to 2. So we're kind of hitting that twice. I know we're saying it here already as an inequality. We're saying it here in interval notation. Our range would be 5 to infinity. Hopefully all that made sense. Okay, so what now? Now we're supposed to actually verify that the function that we found really truly is the inverse of this. So for that, let's get some dotted lines going. Just make a little division down here and then divide this horizontally. And up here in the top, we're going to do it one way. We're going to do f composed with f inverse. And down here we'll do f inverse composed with f. And hopefully both of these will go nicely. So here we want to plug the quadratic into the radical. So we'll have 2 minus the square root of the quadratic function minus 5. The quadratic function is this thing, 2 minus x all squared plus 5. So there we go. Again, these outer parentheses are just placeholders. We can just resolve those parentheses and then let the 5 get canceled by the negative 5. We're now looking at the square root of something squared, so that cancels out. And the square root of something squared, again, is the thing that normally would become absolute value of 2 minus x. But that seems bad. If I allow this thing to just be absolute value, then, well, then what? Then it's not gonna, we couldn't get rid of the absolute value bars and the values wouldn't cancel. So here's where things get pretty tricky. Thinking about your absolute value. If we had an absolute value graph, then normally we would want the right hand side. That's the side for the positive inputs. But think about, again, our function. Wasn't our function defined as the bottom of the radical? It was the negative values of the radical, which reflected and corresponded to the left-hand side of the quadratic. So of my little absolute value, what I actually want is this side, the negative side, which means the function that models that side is not the 2 minus x, but the opposite of 2 minus x. So we know that actually to resolve this correctly on our restricted domain, this thing wants to become the opposite of 2 minus x. And then from there, no, I'm messing up. I'm messing up a little bit, which is annoying. Okay, my bad. Hold on. This is more complicated than I thought, or at least than I wanted it to be. We don't just want the opposite. That's my bad. We need to actually write a rule to model this. And I didn't want to get too deep into this, but maybe I don't need to get too deep into it. It is looking like if we just resolve those bars, then we would get the 2 minus 2, that would cancel, the negative would distribute, we would get x. So yeah, that's actually fine. So we don't actually have to apply negative to it. Ugh. You know what, we could talk more about this in class if it's relevant. Frankly, it's not relevant. Basically, just resolve those absolute value bars because you can, because we're on our restricted domain anyway. So this is going to work out. But then from here, you would get 2 minus 2 plus x. And then you can let the 2's cancel, and you just get your x. Obviously, that did not go as well as I wanted it to, at least as far in terms of my explanation. I keep wanting to address the whole absolute value thing and explain it away, and I keep doing a bad job of it, so I apologize. But let's do the other one. We this time are plugging function f into the inverse function. So starting with the inverse function, which is our quadratic, we would have 2 minus x all squared plus 5, where the inverse function is the radical, so 2 minus root x minus 5. But there's our composition, and then we can clean this up, because again, these parentheses are meaningless placeholders. 2 minus 2 can cancel. We are now looking at negative root x minus 5 all squared. So squaring the negative means the negative cancels. Squaring the radical means the radical cancels, and we land on x minus 5 plus 5. And then we can let the 5's cancel. Okay, had to pause the video for a sec to sneeze. But there you go. Here's your algebraic proof. We did the composition in both directions. We showed that they do both boil down to plain old x, so we do have the right inverse, and everything is hunky-dory. That's number 6. And this video is at 25 minutes, so I think I'll just quit here. And we'll move on to the next ones. We'll make them separate videos again. I think that's been working out. I don't know. You guys can tell me. I assume it's a good thing to just have shorter videos, and you guys watch the ones you want to watch. Anyway, see you later.